somewhere in your house right now, there is almost certainly a bolt, a screw, or a threaded fastener whose exact shape, angle, and pitch was decided by one Philadelphia toolmaker in 1864, a man whose name essentially nobody alive today would recognize, even though his decision touches nearly every mechanized object they own. He did not design the most elegant thread form available at the time. British engineers had already proposed one, rounder and by at least one meaningful engineering measure, arguably more durable. He designed the one that was easiest for an ordinary machinist to cut correctly with an ordinary lathe tool, ground freehand at an ordinary grinding wheel, and he pushed it through American industry not by winning a theoretical argument about engineering purity, but by convincing the single largest railroad in the country to make it mandatory for everything it bought. That decision rippled outward for a century and a half, through 2 world wars, into a 1948 international treaty between 3 governments, and ultimately into the metric threads used on nearly every machine built anywhere on Earth today. And yet the company that made it happen, the company that put his name on machine tools shipped across the world for nearly 100 years, no longer exists under that name at all. It passed through the hands of 6 different corporate owners across the 20th century, until a handful of laid-off machinists in upstate New York decided, entirely on their own, without a Fortune 500 sponsor behind them, that the knowledge was worth saving anyway. This is the story of William Sellers and Company, and of the standard that outlived every single one of the men who fought over it. William Sellers was born on September 19, 1824, in Upper Darby Township, Pennsylvania, into a Quaker family that had been producing inventors and mechanically minded tinkerers for generations. The kind of family where a working knowledge of gears and tolerances was practically inherited alongside the family silver, and where the surname Sellers already carried real weight among Philadelphia's engineering and manufacturing circles well before William made his own name. After a private education arranged by his family, rather than a formal engineering degree, of the sort almost nobody in his trade held at the time, he was apprenticed at 14 to his uncle, J. Morton Poole, who ran a machine shop near Wilmington, Delaware. He spent 7 years there, learning the trade from the ground up, sweeping floors and running lathes long before he ever designed anything himself. And at 21, in 1845, he was hired as general foreman of the shops of Fairbanks, Bancroft and Company in Providence, Rhode Island, then considered the largest steam engine works in New England, an operation whose lineage would eventually feed into what became the well-known Corliss Steam Engine Company. 2 years later, in 1847, Sellers returned to Philadelphia and set up a machine shop of his own, betting that the city's dense concentration of foundries, textile mills, and machine shops would support an independent operation the way Providence's had. A year after that, in 1848, his former employer's associate and his own brother-in-law, Edward Bancroft, joined him as a partner, and the firm operated as Bancroft and Sellers until Bancroft's death in 1855, at which point it reorganized under the name it would carry for the next 92 years. William Sellers and Company, with Sellers' brother John Sellers Jr. and his cousin Coleman Sellers joining as partners, keeping the business, in the way of so many 19th century American machine shops, firmly inside the family. From the start, Sellers approached machine tool design with a philosophy that set him apart from most of his American and European contemporaries. Machine tools built in the mid-19th century, especially in Europe, were often decorated with cast ornamentation, fluted columns, scrollwork, the visual habits of an era that still expected even industrial equipment to look presentable in a certain formal sense. Sellers stripped that away almost entirely, building plain, heavy reinforced iron machines designed purely around function and rigidity, a design instinct that would not become fashionable in industrial design more broadly for decades. One of his earliest and most technically significant inventions was the spiral-geared planer. A planer is a machine tool built to cut large, flat surfaces. It works by clamping a workpiece to a table and driving that table back and forth beneath a fixed cutting tool, in a long reciprocating stroke, the opposite arrangement from a lathe, where the workpiece spins and the tool moves. The problem with most planers of the era was in how that table got driven back and forth. Ordinary straight spur gears, meshing tooth against tooth, deliver power in a series of small, discrete impulses, and at the two extremes of the table's stroke, where the mechanism has to slow down, stop, and reverse direction. That unevenness showed up as a jolt, a moment of chatter, sometimes visible in the finished surface as a faint ripple right where the tool reversed. Sellers replaced the straight gearing with spiral or helical gears, whose teeth engage each other gradually along an angled cut rather than all at once, smoothing the transmission of power through the entire stroke, including the reversal, and producing a noticeably more even table motion and a cleaner finished surface. It was, in effect, the same underlying problem that other machine tool builders would spend the next century solving in other ways. Hydraulic table drives, servo motors, computer control, and Sellers had already found one mechanical answer to it, with gearing alone in the 1850s. He would go on to patent more than 90 inventions over his lifetime, including bolt-making machines, a range of gear-cutting equipment, rifling machines for gun barrels, and improvements to steam locomotive and boiler injectors. But none of them would come close to matching the influence of the idea he presented to a room full of engineers in April 1864. To understand why that idea mattered, you have to understand just how badly American industry needed it. By the 1860s, the machine shop trade in the United States had grown enormous and enormously fragmented at the same time. Almost every shop of any size cut screw threads to its own private convention, its own pitch, its own thread angle, its own notion of how deep a thread should cut and how a nut should be proportioned to fit it. Conventions that had usually been worked out informally by whoever ran the shop and passed down to apprentices without ever being written down anywhere. A bolt made in one shop and a nut made in another, even nominally the same diameter, might not thread together at all, or might thread together loosely enough to be dangerous. And a machine that broke down far from where it was built might sit idle for weeks, waiting for a replacement part custom fitted by hand rather than simply pulled off a shelf. Britain had already addressed this problem after a fashion. In 1841, the engineer Joseph Whitworth had surveyed screw threads from workshops across the country and proposed a single national standard, a 55-degree angle between the thread's flanks, with rounded crests and rounded roots at the top and bottom of each thread. It was adopted widely across British industry through the 1850s and 1860s, powered in part by the prestige Whitworth earned, displaying his machines at London's Crystal Palace exhibition in 1851, and by the Royal Navy's own adoption of Whitworth threads on its engines during the Crimean War, and it saw considerable informal use in the United States and Canada as well through those same decades, simply because nothing homegrown existed to compete with it. William Sellers thought Whitworth had gotten the engineering half right and the manufacturing half wrong on April 7, 1864, as president of Philadelphia's Franklin Institute, one of the country's leading forums for mechanical engineering at the time. Sellers presented a paper proposing an American alternative. He kept Whitworth's basic insight that a national thread standard needed a fixed angle and a systematic relationship between diameter and pitch. But he changed the geometry in two specific, deliberately practical ways. First, he widened the thread angle from 55 degrees to 60 degrees. Second, and more importantly, he replaced Whitworth's rounded crests and roots with flat ones. The reasoning was entirely about what an ordinary machinist, working with ordinary tools in an ordinary shop, could actually produce reliably. A rounded thread profile requires a cutting tool ground to match that exact curve, a genuinely difficult shape to grind accurately by hand, and just as difficult to verify once it is cut, since checking a curved surface against a gauge is inherently less precise than checking a flat one. A flat-topped, flat-bottomed thread, by contrast, can be cut with a simple tool bit ground to two straight angled edges, meeting at a point, something close to any competent machinist in the country could produce freehand at a grinding wheel, and its accuracy could be checked afterward with nothing more sophisticated than a straight edge or a simple thread gauge. Sellers did not stop at the profile. He worked out a complete, internally consistent table specifying the exact thread pitch, meaning the number of threads per inch, for every standard bolt diameter from 1/4 of an inch all the way up to 6 inches, along with standardized proportions for how large a hex nut or bolt head should be relative to its thread diameter. Where Whitworth had solved the shape of a single thread, Sellers had solved the entire fastener as a manufacturable, inspectable, universally reproducible system, covering essentially the whole practical range of American industrial hardware in one document. It is worth being honest about the trade-off buried inside that decision, because Sellers' choice was not simply superior engineering dressed up as manufacturing convenience. A flat root, where the bottom of the thread groove meets its neighboring flank at a sharp, angular corner, concentrates mechanical stress at exactly that corner far more than a smoothly rounded root does. And under repeated loading or vibration, that stress concentration is precisely the kind of detail that starts a fatigue crack. Whitworth's rounded root was, in that narrow sense, the more durable design. Sellers had knowingly traded a measure of long-term fatigue resistance for something he judged more valuable in 1864, a thread form that an under-equipped, unevenly trained American machine shop trade could actually produce correctly and consistently, at scale, without specialized tooling. It was an engineer's compromise in favor of manufacturability over theoretical perfection. And for the industrial economy America was building in the 1860s, it was almost certainly the right trade to make. The Franklin Institute moved quickly. A special committee reviewed Sellers' proposal and formally endorsed it on December 15, 1864, barely 8 months after he first presented it. And the Institute, with Sellers himself sitting as its president through this entire period, began actively lobbying the federal government to adopt the system nationally, rather than leaving it as one more regional preference competing against Whitworth's British Standard and a dozen private shop conventions. The United States government, including the Navy, began adopting the Sellers thread around 1868, a meaningful but not yet decisive endorsement, since government contracts alone still covered only a fraction of the country's total industrial output. The single decision that actually guaranteed the standard's long-term survival came the following year, in 1869, when the Pennsylvania Railroad, by a wide margin, the largest and most operationally complex privately organized industrial enterprise in the country at the time, adopted the Sellers thread as mandatory for its own rolling stock, its repair shops, and everything it purchased from outside suppliers. That single decision mattered more than years of voluntary adoption by individual machine shops ever could have. A railroad the size of the Pennsylvania Railroad operated dozens of repair and manufacturing shops, scattered across a network stretching over thousands of miles. And every one of them now needed bolts, nuts, and threaded fittings that matched a single national specification rather than whatever a given local supplier happened to produce that week. Any machine shop, foundry, or fastener maker that wanted to sell to the Pennsylvania Railroad, one of the largest industrial customers in North America, and effectively a captive market unto itself, now had to retool to the Sellers standard, whether its owners found the 60-degree flat-top thread more elegant than Whitworth's rounded one or not, and whether they had any particular loyalty to a Philadelphia toolmaker's opinion or none at all. Other major railroads and manufacturers followed over the next several decades, less because of any further engineering argument being won, and more because an entire regional supply chain had already reorganized itself around the standard the Pennsylvania Railroad demanded, and it was simply cheaper and easier for everyone downstream to match what the biggest buyer in the market already required. In May 1924, long after its informal adoption had already become near universal in American practice, the standards apparatus that had grown up around American industry formally redesignated it the American Standard Thread, a bureaucratic renaming of something that had already won the argument on the shop floor 60 years earlier. Sellers did not spend the rest of his career resting on that success, and in fact used the credibility it earned him to keep expanding into entirely different branches of heavy industry. In 1868, the same year the federal government began adopting his thread standard, he organized the Edge Moor Iron Company, which grew into the largest plant in the world for fabricating and erecting iron bridges, supplying the structural ironwork for buildings at Philadelphia's 1876 Centennial Exhibition, and most famously, providing all of the structural steelwork used in the construction of the Brooklyn Bridge, a project that would remain one of the most celebrated feats of American civil engineering for the rest of the century. In 1873, Sellers reorganized a struggling operation called the William Butcher Steelworks in the Nicetown section of Philadelphia into the Midvale Steel Company. And under the leadership team he helped assemble there, Midvale grew by the time of the 1876 centennial into what one historian later described as a company as congenial to a scientific approach to industrial problems as could be found anywhere in America, eventually becoming one of the country's leading producers of heavy steel forgings, ordnance, and armor plate for the United States government, a business built on precisely the kind of exacting, repeatable manufacturing standards Sellers had already spent a career trying to instill in the trade. That description of Midvale as a place built for a scientific approach to industrial problems turned out to be more literally true than Sellers could have anticipated, and it produced the company's strangest and most far-reaching legacy. In 1878, a young machinist named Frederick Winslow Taylor took a job as a laborer in Midvale's machine shop, having already trained as a pattern maker and machinist elsewhere in Philadelphia after abandoning plans to attend Harvard due to failing eyesight. Over the following decade, he rose rapidly through the ranks at Midvale, from laborer to time clerk to journeyman machinist to gang boss to shop foreman to, eventually, chief engineer of the entire works, all while completing an engineering degree by night through correspondence courses with the Stevens Institute of Technology. It was at Midvale, starting in 1881, that Taylor began systematically timing workers with a stopwatch, breaking their tasks down into individual motions, and searching methodically for the single most efficient way to perform each one, convinced that the workers he supervised were deliberately working well below their real capacity, a practice he called soldiering. Those experiments became the foundational work behind what he would later call scientific management, and what the rest of the world would come to call Taylorism, one of the most influential and most controversial theories of industrial organization ever developed, one that would go on to reshape factory floors, assembly lines, and management theory across the entire 20th century, for better and for worse. The company William Sellers built to make steel had, without either man apparently intending it, become the birthplace of modern efficiency engineering. Incubated inside the same Philadelphia industrial network that had already reshaped the physical geometry of every bolt in the country, it is a strange kind of double legacy for one man to leave behind: the exact angle of a screw thread, and almost by accident, the intellectual seedbed for an entire school of thought about how factories should measure and manage human labor. Sellers' public standing grew alongside his businesses. He served as president of the Franklin Institute from 1864 to 1867, precisely the years his thread standard won its initial endorsement. And he remained a trustee of the University of Pennsylvania continuously from 1868 until his death, a span of 37 years. He was elected to the National Academy of Sciences and the American Philosophical Society, was raised in and remained connected to the Quaker tradition of his family, and was known specifically as a committed abolitionist in the years before the Civil War. By the time he died in Philadelphia on January 24, 1905, at the age of 80, he held more than 90 patents and had spent nearly 6 decades near the center of American mechanical engineering, respected enough that his name had already become permanently attached, almost anonymously, to nearly every threaded fastener manufactured in the country. The company he left behind kept operating as a respected builder of machine tools well into the 20th century. Its later product lines, including vertical boring and turning mills and precision drill and tool grinders, still carrying the Sellers name cast directly into its machine housings decades after its founder's death, still trading on a reputation for rigid, plain, overbuilt iron that traced directly back to Sellers' own 19th century design instincts. but the ownership chain that eventually took hold of it tells its own separate story about what happens to a century-old industrial name once the founding family and the founding generation are both gone. In 1943, a group of outside investors purchased William Sellers and Company outright, and by April 9, 1947, the firm's historic machine tool division was formally sold to the Consolidated Machine Tool Corporation and physically relocated out of Philadelphia entirely to Rochester, New York, ending 99 years of continuous Sellers-named operation in the city, where the company and the thread standard that made it famous had both been born. The name kept moving after that, passing through owner after owner in a pattern that would have felt familiar to several other historic toolmakers by the second half of the 20th century. Consolidated Machine Tool was itself acquired by the Farrell Birmingham Company in 1951. Farrell Birmingham simplified its own name to the Farrell Corporation in 1963. Farrell was purchased by the United Shoe Machinery Corporation in 1969, an odd pairing of an old New England shoe manufacturing equipment maker with a Philadelphia machine tool lineage. Farrell was folded into the larger conglomerate Emhart Corporation in 1976, which began dissolving off Farrell's various individual machine tool product lines piece by piece over the following years. The exact same pattern of conglomerate absorption and slow dismemberment that had already ended several other historic American toolmakers by that decade. Layoffs at the Rochester plant began in 1982 in the historic Farrell Works, the same facility that had once absorbed the old Sellers machine tool division, finally closed its doors for good. Out of that closure came the last, smallest, and in some ways most quietly remarkable link in the chain. In 1982, a group of 5 former Farrell Corporation employees, all of them recently handed their own layoff notices, decided the accumulated knowledge behind the old Farrell, Betts, and Sellers machine tool lines was worth preserving even without a corporate parent behind it, and founded a small company called Machine Tool Research to service, rebuild, and support that equipment directly for the customers who still depended on it. That company still operates today, out of the same former Farrell facility in Rochester, and since 2018 has been organized as an employee stock ownership company, meaning the workers themselves, not a distant conglomerate, own the business. Somewhere inside that small employee-owned shop in upstate New York sits the last living institutional thread, connecting back to a Quaker toolmaker's Philadelphia machine shop from 1847, a lineage that survived 6 changes of corporate ownership across 135 years, not because any of those owners particularly valued the history, but because a handful of laid-off machinists in 1982 decided it was worth keeping running anyway. There is a particular kind of quiet victory in how thoroughly William Sellers won the argument he started in 1864, and how completely the company that carried his name eventually lost its own. In 1948, more than 4 decades after Sellers' death, the United States, Britain, and Canada finally sat down to resolve the incompatibility that had persisted between American and British threads since Whitworth and Sellers had gone their separate ways nearly a century earlier, an incompatibility that had caused real documented problems supplying and repairing Allied military equipment across 2 world wars. The resulting unified thread standard, adopted jointly in 1948 and 1949, took William Sellers' 60-degree thread angle as its foundation, the same angle he had chosen specifically because it was easier for an ordinary machinist to cut, while adopting Whitworth's rounded root as a compromise, a quiet acknowledgement, 70 years after the original argument, that Whitworth had actually been right about that one detail. Even the international metric thread standard that much of the rest of the world settled on by the end of the 19th century used that same 60-degree profile Sellers had proposed, simply resized to metric dimensions, meaning that today, whether a bolt is measured in inches or millimeters, it almost certainly still turns at the angle a little-known Philadelphia machinist decided on, because it was the easier thing to cut correctly with an ordinary tool in an ordinary shop. Nearly every threaded fastener manufactured anywhere on Earth still carries some trace of that 1864 decision. The man who made it is remembered, if at all, only by historians of the machine tool trade. The company that built his machines and put his name on them no longer exists in any form he would recognize. Kept alive today only by a handful of workers in Rochester who decided, entirely on their own, that some inheritances are worth the trouble of keeping.